So this video is primarily concerning a presentation I did for SUNY Brockport for Scholars Day, um, and it's concerning the Raspberry Pi implementation of what is called the Drowsiness Detector, which is basically just an AI program that was originally made on the computer to identify if an individual is drowsy based on whether or not their eyes are closed or not. And I'll talk a little bit more about that later. But the main point of this presentation is that I took the code from the PC, which the design was written in the PC, but the problem here was that the resource allocation was okay for the PC, but it needed to be adjusted for the Raspberry Pi, and therefore a port needed to be happen. And so, just a brief mention, what the Raspberry Pi is. It's a very widely used piece of hardware nowadays. It's used in prototypes in just any project that could use a small computer, primarily for embedded systems design. You could use a Raspberry Pi for onboard computer. And prototypes it's a very important design for prototypes, because you can, if you have an idea of a small scale program, you can try running it on the Raspberry Pi because the Raspberry Pi has limited resources, and I'm going to talk about that later. So since the Raspberry Pi has limited resources, the current code that we have that runs on the PC, it's going to overload the Pi's resources. It's a little too much. And on top of that, there's some small incompatibilities that have to be addressed. One of those being the Raspberry Pi uses its own camera called the Pi camera. In order to address that main issue, I merely imported a Pi camera module to kind of just handle the Pi camera and just being able to read the camera in general. This is a peripheral on the Raspberry Pi that can be used for computer vision. So the biggest challenge, one of the biggest challenges was trying to prepare the Pi. So the Raspberry Pi has, you have to install a lot of dependencies for the Raspberry Pi, the same way you would the computer, but it's a little bit different on the Raspberry Pi. It's mostly Linux. It's a Raspbian, actually, which is a flavor of Debian. And so this is a lot of dependencies. And these are all required for facial recognition. The biggest dependency that had to be installed was OpenCV, which is a computer vision library that you can use in Python, but it's very demanding. And in total, it took about 2 to 3 hours of compile time just for the OpenCV. And with all the dependencies together, it was like 4 hours for the installing. So my idea was, when I'm preparing the Raspberry Pi, every time I have to, maybe I get a new Raspberry Pi, I have to do more development on, I should just write a script. So I did that. I wrote a bash script and installed all the necessary dependencies for the Raspberry Pi. And that requires no human intervention, so I can work on other projects while the Raspberry Pi is being prepared in the background. And so once I got the Raspberry Pi prepared, I ran into an issue. And that was that I needed to do some optimization for the Raspberry Pi. The code that was originally being used, since it was meant for the PC, it ran slow. The frame rate was calculated at about 0.25 frames per second, which is about 1 frame every 4 seconds, which is very slow. And this isn't really usable for a Drowsiness detector. So that led to 2 changes that I needed to do. One of those changes was the multi-threading. So in multi-threading, just to kind of briefly explain it, I guess just to explain what a normal program does is that it has a main thread and only a main thread. And it does that, or through that main thread, it accomplishes all the computational tasks it needs to do in one process. This can lead to a slower program depending on how many tasks you're accomplishing in a given program. But if you have multi-threading, you can separate that task into what's called multiple threads. And each of these threads share the same memory or resources as the given process or the main thread. And this was what we wanted to do. We wanted to incorporate multi-threading into the Raspberry Pi to increase this speed and increase CPU utilization of the Raspberry Pi. This was really a relatively small improvement. What we did for the Raspberry Pi was we used the camera reading. I'll just go back real quick. The camera was the kind of the second thread, the extra thread that we used. So the camera was reading through its frames with a thread, and then the main thread was responsible for taking the frames that the second thread gave it and did facial recognition computation on it. And so it was a minor improvement, only 1 to 2 frames per second, and this kind of led me to have to do some research on the current code we were given, and I found an updated version of the program that I was using a better model. But when I say better, I only mean better in the sense of it led to faster frames. But essentially, it was an older model, and this was because of less accuracy. And this model was the Haar Cascade classifier. So I want to spend the rest of the presentation just to kind of briefly explain the Haar Cascade classifier, because it was the thing that sped up the camera and led to the actual facial recognition on the Raspberry Pi. So the Haar Cascade classifier is essentially it's a machine learning approach which uses the Viola-Davis algorithm, which is a very old algorithm. And just to briefly mention what machine learning wants to accomplish, usually in machine learning you're going to give, in some approaches of machine learning, you give it a positive image or a set of positive images. In this case, it's my face. So that would be one picture that contained a face. And negative images would be pictures that do not contain a face, to kind of tell the computer, oh, this is something that it does not contain a face. Everything in this picture does not contain a face. So I'll use that when I'm tuning my algorithm. So in this case, I'm using like a trash bag. That's clearly not a face. So the main point of the Haar Cascade, or just the beginning part of the Haar Cascade classifier, are the Haar features. So these features are very necessary for extraction. If you look here, the edge features, the line features, and the 4 rectangle features are the base features that you are kind of looking for when we're trying to identify pixel differences in a face. And what that means is it just darker pixels rather than light pixels. And this is because most of the time when you're doing facial recognition, you want to grayscale the face, so that it leads to less pixel computation. And we need these values for extraction. But in order to do this pixel computation, what we do is we essentially do the difference between the dark pixels and the white pixels. And in an actual image, it's not going to be this apparent. It's going to be a lot of grays and blacks and whites. But after you do this difference, you do a summation of all those differences together. And these are the types of features that we want in order that make up a face for a Haar Cascade classifier. And so it's still a lot of computation because you have to do every single pixel individually, the difference between them. But realistically, if we want to identify a face, we only need a few features. So this leads me to want to talk about the key features in the Haar Cascade, of the Haar features. So the key Haar features, essentially. So this is going to be a lot more similar computation because it's still the difference, the summation of the subtraction of the black and white pixels, but it's primarily associated with these parts of the face. So if you look at the pictures down here, you look at this person's face, right above the eyes is typically darker than right below. So this means that this kind of a simplified version, but this is like a Haar feature. And the second box over here shows that right here, the bridge of the nose is going to be lighter than to the right and to the left of it, or around the eye area. So what this means is that because we really only need the key features, it leads to fewer features. And these features are kind of the eyes, nose, mouth area. That's really all we need to identify a face in a given image. And the kind of I'll just go back real quick. This is going to help us with computation. It's going to lead to a lot less pixel math. And then I kind of want to talk about the classifier part of it. So a weak classifier is essentially each Haar feature on its own, and just kind of trying to use all the Haar feature collections together, or individually, sorry, and using them individually as weak classifiers, it's going to lead to very low accuracy. And that's not what we want for identifying a face. So what we do want is what's called a strong classifier. And this is just kind of combining all the classifiers together, and, combining them to make a strong classifier for the increased accuracy. And one of the ways to kind of incorporate that strong classifier is by doing what's called a cascade of the classifiers. So what this means is the cascade of classifiers goes off the fact that, I guess kind of I want to preface why we want to use the cascade of classifiers, and then I'll explain what the cascade means. So, So the cascade classifier, it's still going to be a lot of computation, but the way we can reduce the computation is by figuring out if the image that the computer's been given is really not a face, and it's not necessary to continue doing computation on the face or on the pixel difference of the face. And because of this, we want that. We want to check if it's not a face because of it's much faster. So what does this mean really for cascade of classifiers? So what the cascade part means is that it's going to require stage passing. So kind of this picture down below, it shows that as you pass stages, you get more and more kind of specific areas of the face to do computation. So at stage 1, there's really this huge general block, and it might be only like 1 or 2 features. In this case, it's just feature 0, and stage 9 here is feature 83, which means that like every stage you're going to be increasing the number of features, and this means that if at stage 0 it's not a face at all, you can immediately stop computation. You don't even have to keep trying to go through the other stages. So it's a sort of a threshold, because you have to pass every single stage in order to finally figure out, what I've been given is a face, because it's going to do a higher amount of computation using a higher amount of features. And overall, this is what makes the Haar cascade classifier. And this is what led to the increased performance of the Raspberry Pi using the Drowsiness detector, because it's an less accurate model, but overall it's a lot faster. Just some validations for this presentation. So with camera resolution, if you use a higher quality camera, it will lead to a slower performance because you are having to do math on a higher level of pixel density. So that's just kind of something to think about when you're doing this. And also camera positioning. In order to do our Drowsiness detector, it had to be perfectly in front of our face. If your face is moved a little bit to the right or to the left, it's not really going to identify it or be able to do the facial recognition. Another thing that you would have to improve is camera lighting. So right now, the Raspberry Pi, using the Pi camera, it can really only be used in proper lighting conditions. The camera that is on the Raspberry Pi currently does have the ability to use night vision, and that's something you would have to incorporate if you wanted to further develop this technology. And the last validation is hardware capabilities. It's a lot more limited in hardware because of the Raspberry Pi, which means that also means a limited model use. So if you want to improve the accuracy, you might have to take out performance speed. You might have a slower frame rate, but you don't want the frame rate to be too slow, like I showed before, where if you use the base computer model, it's going to be about 0.25 FPS. So this leads to really, you want to find a medium between accuracy and speed if you can when you're doing this. And so just a brief discussion of the shortcomings. We found that people have a lot of different resting eye aspect ratios, depending on ethnicity. So you would have to probably tune it to the user if you wanted to properly identify the eye aspect ratio. And if an individual doesn't really have knowledge of Python programming, they wouldn't be able to use this device in its current state. And like I said before, it's limited hardware resource on the Pi. leads to some complications. So the next step for me is I'm going to be doing more research in the summer with Dr. Ning Yu, the faculty member who helped me with this research, and it's primarily just concerning TensorFlow with Raspberry Pi. But these are my references and app index, and that's my presentation. Thank you.